Bismillahirrahmanirrahim. We're going to start the topic of logical addressing in the network layer. First, we see what is an internet protocol, right? So, an internet protocol, an IP address, is a numerical label assigned to each device connected to a computer network. So, whenever any device is connected to a computer network, it gets assigned an IP address that uses the internet protocol for communication that you have already studied. An IP address serves two main functions: host or network interface identification and location addressing. We're going to see that shortly. The IP version 4 defines an IP address as a 32-bit number. However, because of the growth of the internet and the depletion of available IPv4 addresses, a new version of IPv6 that uses 128 bits for the IP address got standardized in 1998. IPv6 deployment has been ongoing since the mid-2000s. IP is a protocol within the internet layer of the TCP/IP protocol that you studied last week, which is in the network layer of the OSI model, which defines addressing and how individual messages are routed to their intended destination. So IPv4 addresses. An IPv4 address is a 32-bit address that uniquely and universally defines the connection of a device. For example, it can be a computer or even a router to the internet. So you can see the IPv4 address over here. So IPv4 addresses are unique and universal, and it is 32 bits long. So if the address is 32 bits long, so you know well from your digital logic concepts that if you have 32 bits, the total address space that it can cover is 2 power 32, which is this number, which is huge. So the notation is usually the binary notation. As you can see that there are ones and zeros over here. So you can just count them: 1, 2, 3, 4, 5, 6, 7, 8. So 8 bits make a byte. So you can see that there is 1, 2, 3, 4. So 4 bytes are there. So 32 bits makes 4 bytes. Since there are 8 bits in 1 byte, so there are 4 bytes in an IPv4 address. So this is the binary notation of that. And you can see this is the decimal notation. So whenever we're going to denote in the decimal numbers, it's usually like that. We put a period, or you can say a full stop. So that's 128.11.3.31. So that 128 basically is this byte. So, and this corresponds to this 11. This binary number corresponds to 3. You can see that there is 1 1 over here. So 1 1 in binary is basically 3 in decimal. And you can see that there are 5 ones over here. So 5 ones correspond to the 31 in decimal number system. So this is the convention that is usually used. You must have seen this convention that there are 4 bytes, and when converted to the decimal number, they are usually represented in the form of a full stop, or you say a period. So there are 4 bytes corresponding to the 32 bits of an IPv4 address. So let's see. Change the following IPv4 addresses from binary notation to the dotted decimal notation. So you can see that obviously this is a valid an IPv4 address. So if someone asks you to write the corresponding decimal version of that, so you need to consider the 8 bits starting from right or from the left. It does not make any difference. And you have to mention the corresponding decimal of that. So obviously you can see that this is the 1 on the 0th position of the 4th byte. So 2 power 0 is 1, and 2 power 7 is 128. So 128 plus 1, 129. So if you don't have a calculator, even then numbers like that are quite easy to compute. You can see that this is 1011. This is quite simple. That is 11 in decimal, and similarly this is 11, and this is 239. So if the number is complex in the sense that it is not easy to compute without the calculator, you can use a calculator, but make sure that you consider the 8 bits only. You don't have to consider more than 8 bits. So this 8 bits corresponds to this 129, this corresponds to 11, this corresponds to 11, and this corresponds to 239. So this is the IP address of whatever the device there is in the network. Similarly, as far as this B is concerned, again, you have to consider each 8 bits separately, and then you have to write the corresponding IP address of that. So in the next question is the change the following IPv4 addresses from dotted decimal notation to binary. So now we have the decimal number or the decimal number representation of the IP address, and we have to convert this to the corresponding binary number. Again, as far as 111 is concerned, you have to convert this decimal number to the corresponding binary, which is this. Again, you can compute it without calculator or with the calculator, it's up to you. And then the next one, 56. Keep in mind that you have to mention 56 in complete 8 digits. So you don't need to mention like 111000, and you can say that this number can be represented in 6 bits. You have to represent that in 8 bits. In order to complete the 32 bits, you have to consider each byte, right? So 8 bits corresponds to 1 byte. So there should be 8 bits, then 8 bits, then 8 bits, and then 8 bits. So each of these corresponding decimal numbers should be converted to the binary numbers like that. Then we have 2 to 1. 2 to 1's binary representation is this. 34's binary representation is this. 7's binary representation is this. So make sure you count the number of zeros and you do not miss out on any number, and that's how you do it. Next, find the error, if any, in the following IPv4 addresses. So first we see that 111.56.040.045, then .78. So there should not be any leading zeros. So you can see that here there is 045. So it is the rule of an IPv address that there should be no leading zero. So this is an error. So this is the error that you have identified. Next, part B, 2 to 1.34.7.8.20. So you can see that there are 1, 2, 3, 4, 5 numbers. So 5 numbers obviously are more than 32 bits because each number corresponds to 1 byte and 32 and 8 bits. So here you can see that there are total 5 numbers. You cannot have more than 4 numbers. So this address is invalid. This address is invalid. Next, 75.45.301.14. So you can see that this looks valid, this looks okay, this looks okay, but 301, each number needs to be less than or equal to 255. A number cannot be greater than 255. Why? Because you have total of 8 bits. You have total of 8 bits. It means the maximum number that you can represent is 255. And obviously for 301 bits, you need to have more than 8 bits. And since a number greater than 255 cannot be represented in 8 bits, it means this is not a valid address. Next, in part D, you see that there are 111000010. It looks like if this is a decimal number, it's a huge number. It's not a valid number. But apparently, he has written a combination of a binary and decimal, which is not allowed, right? So either a number should be displayed in the binary representation or the decimal representation. So this is an invalid address. So in all of these 4 cases, you have seen different kinds of permutations in which the addresses are not valid. Now we are coming to more interesting things. So I want you to pay close attention. Now we're going to see the classful addressing scheme. This is one scheme of assigning addresses, right? So in classful addressing, the address space is divided into 5 classes, A, B, C, D, and E. So you need to have some patience in order to go through this stuff because few things, we will deal with those things a bit later. So the complete, package of this classful addressing will be clear to you once you go through the next slides as well, right? So the thing to take in this slide is that there is a class of addressing scheme that is known as classful addressing scheme. And in that case, we have 5 different classes of addressing schemes. So one is class A, one is class B, one is class C, one is D, one is E. In class A, the first byte is always 0. Sorry, this is the first byte, this is the second byte, this is the third, and this is the fourth. In the class A, in the first byte, the first bit is 0. In the first byte, the first bit is 0. In class B, in the first byte, the first 2 bits are 1 and 0. In class C, and in the first byte, you have the first 3 bits are 1, 1, and 0. In class D, they are 1, 1, 1, and 0. And class E, there are 1, 1, 1, and 1. And if we shift to the corresponding dotted decimal notation, we see that in class A, the first byte is usually represented by numbers between 0 and 127. So these things will be clear to you shortly, inshallah. So wait for that. In class B, the number in the first byte is between 128 and 191. In class C, the number in the first byte is between 192 and 223. In class D, the number is between 224 and 239. And class E, the number is between 240 and 255. So this is how the address space is divided in classful addressing scheme. Let's move on, and then we will get back to this later as well. First, let us solve a very easy example. The question is, find the class of each address. Find the class of each address. So we have this IP address. So we have been asked that, what is the class of this address? So we can see that the first bit is 0. So you have seen this short just a while ago, that if the first bit is 0, we have class A. So you can see that the first bit is 0 over here. It means this is a class A address. All right. Next, in the next IP address, we see that the first bit is 1. Okay, the first bit is 1, but class B also has the first bit as 1. Class C also has the first bit as 1. Class D, E, all of them has first bit as 1. So let's see what the next bit is. The next is 1 and the next is 0. The first 2 bits are 1 and the third bit is 0. So we have just seen that if the first 3 bits are 1, 1, and 0, it means the address is a class C address. So 1, 1, and 0, it means this is the class C address. Next, let us see. The number is, the IP address is now given in the decimal notation. And the number in the first byte is 14. The number in the first byte is 14. So you can see that this is a class A address, because if the number in the first byte is between 0 and 127, it means this is a class A address. So this is if the first byte is 14, it means this is a class A address. Next, 252.5.15.111. The first byte is 252. So you can see that 252 means this is a class E address. This is a class E address. Let's move on to classes and blocks. So now I want you to pay even more close attention. The classful addressing wastes a large part of the address space. Okay, class A, class B, class C, class D, and you can see that we have different classes. And then we have some blocks, then we have some block size, and then we have some kind of application written over here. So first of all, you need to understand what is the meaning of the number of blocks and then the block size. This concept will be clear to you once you do few examples, and then we will again come back to these slides. But for the time being, let us try to understand what is the meaning of the number of blocks and block size. For example, you live in some housing society. You live in some housing society, and there are different kinds of blocks in that, right? So you live in, for example, you say you live in Johor town, and then you have some blocks of that. You say A block, B block, C block, A, B, C, D, E, F, G, H, I, J. You know, there can be number of blocks. And then in each block, there are different number of houses. So you say, I live in Johor town, block A, house number 15, right? So This corresponds to the number of blocks corresponds to, or create an analogy of the number of blocks with the block of the housing society, and create an analogy of the block size with the number of houses in that block, right? For the time being, this is enough. So let's move on and we will come back to that in a short while. In classful addressing scheme, an IP address of class A, B, C is divided into net ID and a host ID. So there is something known as a network ID, and then we have a host ID. The net ID determines the network address, while the host ID determines the host connected to that network. So you have seen this in class A, for example. The first byte is net ID, and then byte 2, 3, and 4 are host ID. So you have seen this a little while ago, that only the first part or the first byte is mentioned in the yellow, and the next 3 are given as white. And for the class B, the first 2 are shown in the yellow and the next 2 are shown in the white. And similarly for class C, the first 3 are shown in yellow and the last one is shown in white color. So basically the reason was that the color in the yellow was depicting the network ID and the color in white was showing us the host ID. We're going to see that what network ID and host ID means. In class A, byte 1 is for the network ID, byte 2, 3, and 4 is for the host ID. For class B, the first 2 bytes are for the network ID and the next 2 bytes are for the host ID. And similarly for class C, the first 3 bytes are for the network ID and only the byte 4 is for the host ID. Okay, so question. Each class is divided into blocks. We have seen that each class is divided into different number of blocks. The number of blocks in a class can be calculated by the number of bits in the net ID. The number of bits in the net ID will tell you how many number of blocks are there in a class, right? So let us see. Class A has 1 byte, 8 bits net ID. You have just seen that. Class A has 8 bytes of net ID, right? So class A has 1 byte, that is 8 bits net ID. And from the binary notation, we have seen that class A address starts with 0. We have seen that in case of class A, the first bit of the first byte starts with 0. So there are 7 bits that are left in case of network ID. Since the first byte is for the network ID, but we have fixed the first bit of that, it means we are left with only 7 bits to play with, right? So there are total 7 bits that can be changed out of those 8 bits that we allocated to the network ID. So the total number of blocks in that case would be 2 power 7. 2 power 7, and 2 power 7 is 128. 128. So I'm repeating this. In case of class A, the first byte is dedicated to the network ID. And in the first byte, the first bit is also fixed. It means you are left with the 7 bits of the first byte. It means you have only 7 bits to play with. So how many combinations are there in 7 bits? 2 power 7 is 128. So total number of blocks in that case would be 128, right? Okay. So how many bits for the host ID? There are 24. So there are 3 bytes or 24 bits for the host ID in class A, right? So the total number of hosts in each block is 2 power 24. That is this bigger number. So 24 bits for the number of hosts. So there are how many blocks? There are 128 blocks. And for the host ID, we had 24 bits, right? So there are 24 bits, means 2 power 24, this number for the corresponding number of hosts. So you can say that there are 128. So I'm creating the same analogy that I just spoken before. I live in Georgetown. There are 128 blocks in Georgetown. In each block, there are these many houses, right? So each house has a unique address in that case. So how many total number of houses are there? how many total number of houses there. Since there are 128 blocks and each block has these many addresses as hosts, the total number of addresses in that case would be 2 power 24 multiplied with 128, this number, whatever this number is. It's a big number, huge number, right? So again, I'm creating the same analogy. You live in your town, it has 128 number of blocks. Each block has 2 power 24 number of houses, right? So the total number of addresses would be, or the total number of houses in the case of the society would be 128 into this number. So these many cases would be, these many addresses can be assigned in case of class A. So let's get back to this. You see that in class A, the number of blocks are 128 and the number of block size is this number, right? So you can see the number of blocks is now clear to you and the block size is now clear to you. Let's move on to class C. And so in case of class C, there are 3 bytes dedicated for the network ID. So you have just seen that in case of class C, you have byte 1, byte 2, byte 3, that is 8 plus 8 plus 8 bits for the network ID, right? So there are 24 bits that are dedicated to the network ID. But again, you have seen that shortly that in case of class C, 110, that is the first 3 bits are fixed. So we are left with how many bits? 24 minus 3, we are left with 21 bits. So we are left with 21 bits. So 2 power 21, these are the number of blocks that can be allocated in case of class C addressing. And there is only 1 byte left for the host ID. There is only 1 byte left for the host ID. And since 1 byte is 8, so 2 power 8 is 256. So only 256 hosts corresponding to 2 power 21 number of blocks. So we have first block, and for first block we have 256. For the second block we have 256, and so on and so forth till 21 blocks. And these are the number of addresses. Total number of addresses in that case again would be 256 multiplied with 2097152, which is this number, right? So basically this corresponds to the 12.5% of the total IPv addresses if we calculate the total IPv addresses. So this is the fraction of the total class C addresses in case of class C addressing scheme in IPv4 addressing. Let's do a very important example. There are 128 blocks in class A. First, let us just summarize what we have just discussed, and then we will move on to the example. There are 128 blocks in class A. So only 128 organizations can be assigned class A address, but each block has these many hosts. So what is the meaning of all that? So just compare that analogy of housing scheme now to this, to the real world example, what it really means to have these number of blocks and these number of hosts. So 128 blocks and this number for the host. What is the meaning of that? The meaning is that there are 128 blocks in class A. So 128 organizations can be assigned class A address, but each block has this many hosts, which means the organization needs to be really huge to consume all the addresses in the block. Because there are 128 blocks, it means 128 or different organizations can be assigned. So let's suppose you have one such kind of an organization, and that organization can then assign this bigger number to, for say, its employees or the computers connected to that. This is a huge number. It means the organization need to be very huge in that case. In case of class B, there are 16,384 blocks in class B. It means these many organizations can be assigned class B address. And there are 65,536 hosts in each block, which means in each organization, again, it should be quite huge to consume all the addresses in the block. Now coming to class C, it has these many blocks. So total, these many organizations can be assigned Class C address, right? But only 256 hosts in each block, which means the organization must be quite small. You have just seen that. You had these many blocks and these many hosts, 256 hosts only. So say an internet service provider, right? So it is assigning addresses to different organizations. So say your university. So for that, in that case, 256 is a small number. Not many students, only 256 students, for example, are given some kind of computer. So only these many addresses can be assigned to them. So this is not suitable for say a university or quite a company of a significant mass. It cannot be assigned a Class C address in that case. This is the reason why a lot of addresses are wasted because of classful addressing scheme. You have seen that you are sort of bounded to this mechanism. So that's why the classful addressing scheme in IPv4 is creating a lot of wastage. Class A address, for example, just see that Class A address can be allocated to 128 organizations. Yes, which sounds quite okay. But each of these organizations must have these many machines or hosts, which is not impossible, yes. But again, for example, if you are left with say 2000 addresses, even then that's quite a lot of wastage. Why Class C address can be assigned to a lot of organizations? Yes, Class C can be assigned to a lot of different organizations. But if an organization gets a Class C, it cannot have more than 256 computers in that case. So that's the drawback. So this is sort of a trade-off, and you have to live with that trade-off. And that is why classful addressing scheme is not very suitable, and you have to see the classless addressing scheme.